Welcome to Soil Extractor Engineering Problems YouTube channel. So now we are going to present the third part for this simulation of a group of 9 piles in soils. So in previous videos we have defined the geometry in the first place, and we have defined as well the materials for the group of piles and for the 2 layers of soil we're going to resolve. And now, in this video, I will work with the static structural analysis in ANSYS Workbench to define the loads, to define the restriction or control conditions, to allow the software to set the connection that will work as an interaction between the group of piles and the soils. And we are going to talk a little bit about the meshing as well when we solve this problem by finite element methods. So I'm going to use a static structural because it's the simplest way to solve a problem like this. This is not the most realistic again because maybe we should introduce more complexity, but as a first attempt, I think it's good enough and it's a good example to follow. So I will, once I open a static structural, I will connect the geometry I have created with this module in here, and I will connect the engineering data with the data of my materials to this module to capture them and to define them in the static structural environment. So once I do that, I can double click in model and I will open the environment where we're going to work from now. So this usually takes a little bit of time because this software is powerful, has many elements, and is demanding in terms of processing. So let me just see what is going on in here. So for some reason, I have a problem. I will close it and I will open again. Probably it's going to be open twice or something like this. No, there was some sort of error. So let's try it again. So I will double click in model again one more time. This software is very temperamental, so sometimes you will have problems that will be solved in only one way, basically closing and open again, or starting your project from scratch. Because as I said, it's a software that is very demanding in terms of hardware, so sometimes you need to be patient in order to be successful. So okay, apparently now the environment is open, so we have recovered the geometry from the design modeler where we have created this geometry, and we have 3 elements, so the piles group and the layer 1 and layer 2 of soils. So because I have deleted in the previous video the properties of the material structural steel, there is nothing attached to this geometry. So the first thing we can do is to just hide this body, and in order to see that the piles group is precisely the group of 9 piles and the cap, and I will assign the material reinforced concrete we have created before. For the layer 1 of soil, I will now show I will assign the soil 1, which is the material I have defined for the first layer, and for the layer 2, I will assign the material soil 2. And now we have assigned all the materials to our problem. So the materials are here, so you can see the parameters we have defined it before in the structural analysis, static structural. And as I mentioned, the connections will be automatically defined. So there is a connection created between the piles and the soil because there is a small gap of a millimeter that we have defined during the creation of the geometry. And there is, of course, a contact between the 2 layers of soil because we have created as well a gap of a millimeter. So if we click in structural, static structural, the first thing we can do in terms of contour conditions is to say that the bottom of this geometry will be fixed. So I will click in fix in here, I will select the face at the bottom and I will apply. And doing that, automatically this face will be fixed in this three-dimensional space. And this is the first condition I will impose to my geometry. And because there is continuity in the soil around this region of the space I'm analyzing, I will impose as a restriction as well that the displacement in the y direction is 0 in this face, and these other two faces in here. In order to impose this contour condition, I will click in displacement. I will then click in this face, and with the control in my keyboard, I will select multiple faces. So all these four faces will have restrictions in terms of the displacement in the y direction that will be equal to 0. And I will do a similar thing to the other faces in the perpendiculars to the x direction. I will say that the displacement in this direction is equal to 0, because this is a sensible thing to do if you are thinking about the continuity of the soil, because we are just considering a portion to do this analysis. So in the x direction will be equal to 0. So with this, I think we are going to have enough for this example. And what we need to do in the next step is to apply some sort of loads, because without loads, we are not going to have any equation to resolve. So I will choose to introduce a pressure directly in here, because it's simpler, and for this example will be enough. I will apply, and I will say that the pressure will be 1 megapascals. So I have set then a load, I have set the restriction or contour conditions, the connection had been created automatically by the software, I have assigned the materials to the geometry, and now what I'm going to do is I'm going to check the mesh of this problem. So in the first place, what I'm going to do is I'm going to click in mesh, and I will say generate mesh to see what the software offers in the first instance. So as you see, then if you have some experience using finite element methods, this mesh is necessary in order to produce the system of equation that will be solved to resolve the problem in terms of displacements. So because we need to capture variation of the stresses, strains, and other variables in this problem, it's good to have a good number of elements to be able to capture the solutions with this element, because the bigger is the number of elements, the bigger are the chances that you capture with better approximation the results of your problem in the post-processing, and have better possibilities of having a more accurate solution if you have a greater number of elements. The first problem I see in terms of meshing in this particular problem is that the cap, if I'm interested in analyzing, for example, the stresses in the caps have only a few elements. So this means that maybe it's a very good idea to have certain control in the size of these elements in the cap. On the other hand, if we just hide this and these layers of soils, what we can see is the meshing of the piles. And remember that when you mesh a problem to be solved by finite element method, you are replacing the original geometry by elements. So these elements are too big, as in this case, you are losing the true geometry of your problem. It's true as well that the geometry we have created in the design modeler is an approximation, because in reality the geometry will be different. But in order to have consistency and to try to respect the geometry we have created in design modeler, it's very good idea in this case to change or to have certain control in the size of the elements. to improve the shape of these piles we have created. So what I'm going to do is I'm going to show you something very simple, because the techniques that you need to improve in mesh could be as complex as you want, depending on the problem. But in this case, what I'm going to do is I'm going to click in mesh, and I'm going to just define the size of these elements, let's say for this, not for this face, but for this solid directly. So I have selected the solid, so this is my selection for the control of the size of the elements, and I will say that the elements will be no more than 150 millimeters in size. So it's an average size because this is a three-dimensional element, and I will remesh to see if I improve the mesh in the way I want. So what we can see now is that with this size control of elements, we have improved considerably the density of the mesh, and now the mesh is reproducing with accuracy the shape of the piles and the shape of the cup. So we have enough elements to capture the different variables that will be the results of this problem. So we can go to check now the sizes of the elements of these layers of soil we have represented in here. So this there is another problem that I see here, that the elements are tetrahedron for the first layers and are hexahedrons for the second layer. It's not the software will be able to run the calculations anyway, but in order to improve the accuracy and the consistent and the aspect of the appearance of the mesh, maybe it's good to introduce another control of size. For example, I will say that this mesh will have another sizing control for these two layers of soils, and the maximum size in this case will be something like 500, for example. So I will remesh to see if this improves the mesh I have originally. Of course, now we have a better mesh. We still having the problem that we have tetrahedrons in the first layers and hexahedrons in the second layer, but the mesh have improved considerably in terms of density. So we have much more points now to represent the solutions of this problem. But remember that the bigger the number of elements, the bigger will be the number of Gauss points in every element and in the whole problem. So the bigger will be the number of equations you have to resolve. In this problem, because it's simple and we are not using a crazy number of elements, the software will be able to resolve the problem quite quickly. But in real application, we need to be careful, and we need to keep a balance between the number of elements and the number of the power we have from the computer to solve the problem. So, but continuing improving the mesh, what I'm going to do now is I'm going to introduce another control of the mesh, and I will basically set the method for meshing, because at the moment the software has full control on the method used. So I will say that I will introduce this control in these two layers of soils, and instead of allowing the software to decide by itself what to do in terms of the method applied, I will say that I want tetrahedrons everywhere to have a consistent mesh. So I will generate again the mesh to see what I got after this control being set. As you see, the more restrictions you introduce, the longer it takes to the software to mesh the geometry, of course, but the mesh is a better quality now, and I'm happy now because I have a nice size and a nice distribution and a consistency between every single part of the geometry of this problem. So being solved the problem of the mesh, what I'm going to do to have something to show as a post-processing in the first instance, I will select in here probably the most interesting thing to be analyzed in a group of pi, which is the deformation in the vertical direction, which is the Z direction in this case. And For now, just because it's the first run, I will keep this as it is, and I will say solve the problem. So at this stage, the software will take all the information we have introduced in these problems, the load, the restrictions, the size of the elements, and the distribution of the elements in the mesh, the material properties, and any other thing we have defined as a geometry, and the software will write or build a mathematical model, as you can read right now. This is what the software is doing. So it's generating the system of equation that has to be resolved. Now the software is preparing the mathematical model and is being ready, to resolve the system of equation that is going to be a big system of equation to be resolved. So the solver of the software, the core of this software, is starting now to solve, as you see, the mathematical model, or this. You can think in a group of thousands or tens of thousands equation that has to be solved simultaneously. In a few seconds, in this case, because the problem is not too complex, the software will be able to resolve this problem in terms of displacements in the first place, and will show us the deformation in the Z direction, which is the solution I have chosen to show in the first instance. Now the results are being written. So just in a few seconds, we are going to see the first results of this problem. So a few more seconds, and we will be able to see something nice. So now the software has resolved the problem. There wasn't any issues, any warnings, any problems to take care of. And this is what we are showing as a post-process, just the deformation in the Z direction. The deformation is usually presented in a scale that is magnifying the deformation. So if you want to see the true scale, you can change it in here. So the deformation is not too much in this case, because the load I have applied and because the properties have imposed in this model. So we have a deformation of only 20 millimeters. But of course, this will change depending on the setting of the model. So in terms of post-processing, it's a good idea sometimes to use the power of the software to show in different ways the solution. For example, a trick I like to use in many situations is to create a section plane. So for example, what I'm going to do, I'm going to hide this part of the model, and I'm going to hide the other layer of soils as well. I will position the group of piles in this way, and I will create a section plane that crosses the piles in the middle. So in this way, what I will be able to see is, if I show again all the bodies, is the solution, but the solution inside the three-dimensional model, which is very useful for the purpose of the analysis. And because this is a problem of soil structure interaction, I can see the structure and I can see as well the soils. There are many ways of showing the solutions, and there is several ways of showing the post-process in order to interpret what is going on. Yes, I don't want to see the exterior, actually. Section plane is what I want to see. So you can play by yourself and to see what are the options. You can show the elements or you can hide the elements. There are many things I can make another video to talk about post-processing in the future. But for now, this is something that is good enough to show, let's say, the solutions in some way. So this is in terms of settlements, let's say. But of course, in the post-processing, just to start discussing the post-processing, you can show other things, many other things. For example, you can show the equivalent von Mises stress if you want. You can show any other component of the stresses. You can show any the shear stresses, for example. You can show the principal stresses. And what you are going to notice now, once I click in solve, is that the solution, it doesn't take a lot of time, because actually the model is already resolved it in terms of displacement. So it's very easy for the software to resolve the stresses and strain, because the software just apply the relationship, the constitutive equation that allow the software to calculate the stresses in function of the strains of the displacements, and the strain in function of the displacement. So using explicit expressions is relatively simply to find these solutions. Another thing you can do in order to see with more clarity what is going on in this group of piles and soils is to show, for example, the stresses only in part of the geometry. So for example, I will choose to clear the data for this equivalent stress in here, that is showing this equivalent stress in the whole group of geometries, and instead I will say that the equivalent stress will be shown only in the soil. So I will run again, and now you can see the distribution of the von Mises stresses just in the soil, independently of the piles. And like this, you can set all sorts of post-processing. As I said, another video will be made to explain the possibilities. But for now, I think this is a good example to see how to set up a simple problem of soil-structure interaction for this group of 9 piles in 2 layers of soils with different elastic properties. The limitations of this model, of course, are that the model is linear elastic and isotropic for the piles and for the 2 layers of soils, but it's a valid model that you will find in the literature, and there is many methods, many classical methods that use elastic approximation to solving the problems. We are going to add more complexity in future videos in terms of post-processing, and we're going to talk about a model that can be, for example, orthotropics with different properties in different directions, so no isotropic anymore. We can talk about plastic models in the future. So I hope you have enjoyed the video. Thank you very much for watching.